Graph convolutions are permutation equivariant and stable to absolute perturbation. But absolute perturbations are pointless, since they can arbitrarily alter the topology of the graph with no change in the absolute distance measure whatsoever. In this segment, we will introduce the relative perturbation model that ties the changes to the underlying graph support, and we will prove that both graph convolutions as well as graph neural networks are stable to relative perturbations. Recall that we measure distances between graph filters modulo permutations. And what we want to know is how changing the graph support affects the output of a filter. To measure the distance between S and S hat, we now consider the set of relative error matrices. This is the set of all matrices E such that, when multiplied with the shift operator S and added back to S, they yield a permutation of the other shift operator S hat. The relative perturbation distance between shift operators S and S hat can then be defined as the norm of the matrix E with the smallest operator norm among all matrices E in the relative error matrix set. Note that now the size of the perturbation is tied to the topology through the multiplication of E with S. To quantify the effect of the shift operator on the output of a graph filter, we will proceed again with an analysis in the frequency domain, a trademark of signal processing. Recall that the effect of a graph convolution in the frequency domain is to rescale the ith frequency coefficient tilde x sub I by a corresponding value h of lambda I given by the filter and the ith eigenvalue of the support, yielding the ith frequency of the output tilde y sub I. We will restrict our attention to the class of integral Lipschitz filters. These are filters whose frequency response satisfies that lambda times its derivative is bounded by a constant c. The plot shows an example of a bank of integral Lipschitz filters centered around different values of lambda. Integral Lipschitz filters have to be wide for large lambda because if lambda is big, then h prime of lambda, its derivative, has to be small. But they can be thin for low lambda because if lambda is small, then the derivative h prime lambda can be big. Now, these filters are of interest because they are the ones that are stable to relative perturbations. The theorem states that graph convolutions are stable to relative perturbations. Given two graphs with shift operators S and S hat such that their relative distances are smaller or equal than epsilon, then integral Lipschitz filters with constant c satisfy the following. The difference in the output is bounded linearly by the distance between the shift operators. The bound depends on the filter through the integral Lipschitz constant c and on the perturbation model through the eigenvector misalignment constant delta. We remind you that the constant delta depends on how different are the eigenvectors of the shift operator S and that of the relative perturbation E. Knowing more about the perturbation E will certainly allow us to compute better values of delta. In any case, this constant is always bounded by 8 due to the unitary nature of the eigenvector matrices. We emphasize that this bound is universal for all graphs with the same number of nodes n. The main theorem of this segment states that graph neural networks are stable to relative perturbations. Let S and S hat be the corresponding shift operators of two graphs such that their relative distances are smaller or equal than epsilon. Let phi be a GNN with L layers and F features per layer and with integral Lipschitz filters with constant c. Then it holds that the difference in the output between two GNNs with the same filter types but running on different graphs is bounded linearly by the distance between the shift operators. The bound depends on the filter through the integral Lipschitz constant c and on the GNN architecture through the number of layers and the number of features on each layer. It also depends on the perturbation model through the eigenvector misalignment constant delta. We emphasize that this bound is universal for all graphs with the same number of nodes n.